I started section 14.7 in class today, and I'm going to finish things up with you on this video. So just to remind you of where we were looking at this equation right here, this expression right here, where we're supposed to set up and evaluate the indicated triple integral. And we'd gotten to the point where we set up the integral, but we hadn't evaluated it yet. So that's where we're going to go from here. So I'm going to copy this to the next slide, and we will evaluate this next. Alright, so I think that in class, some of you had already noticed that this is actually the integral of p cubed, rho cubed. Sine phi to rho to phi to theta. And we're going to start with the innermost integral. So the integral of p cubed, of course, is 1/4 p. I'm sorry, I keep saying p. I'm tired right now. Rho, of course, 1/4 rho to the 4th. The sine of phi, of course, stays. And we're evaluating this from 3 down to 0. If we plug in the value of 3, we're going to get 81 over 4. Of course, if we plug in 0, we get nothing. So this is 81 over 4 sine phi. And then we're going to go back and we're going to put the limits of integration from 0 to 2 pi. And from pi thirds, pi over 3 to pi. And I think that this is supposed to say pi over 2. Carried away with my numbers there. This is pi over 2. There we go. That's better. And this is d phi, d theta. Alright, so going from here now, we're going to integrate with respect to phi. So the integral with respect to phi here is the integral, of course, of the sine of phi, the 81 over 4, which actually we could put at the very front if you'd like. So I'll just ignore it from right there, and we'll put the 81 over 4 at the beginning like we have in some of our other problems. Alright, so the integral of sine phi would actually be negative cosine of phi. And we're evaluating at pi down to pi halves. So the evaluation at pi, of course, is actually going to be -1, but then it's times the negative at the beginning. So right, this is negative of -1, and then minus, and then I need the cosine of pi halves, which is actually 0. So what we've got right now at this point is actually just the value of 1. And of course we need the regular integration that we were just working with over here for the outermost integral. Alright, so we're going to go to the next slide. I'm running out of space on this one. So now we're going to have 81 over 4 integral from 0 to 2 pi of 1 d theta, or just d theta. And of course this works out to 81 over 4 theta. Evaluate 2 pi down to 0, which would give me 81 over 4 times 2 pi, or 81 over 2 pi. And then we're actually finished, and that's our triple integral value using the spherical coordinates. Alright, we're going to change the direction slightly. It's going to look a lot like what we did in cylindrical coordinates as we keep changing these directions slightly. We're going to use an appropriate coordinate system to find the volume of the given solid. So what we're actually doing, this will actually result in volume because of basically because of the fact that we're just integrating over the region, not integrating of a function of the region. So we're going to take a look. This is number 4. And this is the solid. Below x squared plus y squared plus z squared equals 4. Above, z equals the square root of x squared plus y squared. And between, y equals x and x equals 0, with y greater than or equal to 0. All right, so clearly this is spherical coordinates because we have x squared plus y squared equals z squared. Plus z squared equals 4. So this piece of information right here automatically lets us know that rho is equal to 4. Square root of 4, excuse me, so 2. Right? Rho squared equals 4, so it's 2. The other thing that I'm going to draw on, and it's not an example that I've done, but it is an example you can reference in your book, is that this other equation, z equals the square root of x squared plus y squared, it's actually the equation of a cone. And it's a cone, of course, above the x-axis because the z value is positive because it's a positive square root. So this is a cone opening up, so imagine like an ice cream cone or something like that as your image. So as we take a look at this, in fact, I will go ahead and on the next slide just put in the picture that you can sort of think about from this particular argument. All right, so you can see on this picture the yellow part is the cone that's going down and through this blue ball shape right here. And the blue ball shape is in fact exactly what our x squared plus y squared equals z squared look like. However, on this particular graph, it was actually, this is not the actual equation we had, because ours is actually centered at the origin. So this one's actually centered, looks like maybe 1 unit above the origin if it's a unit circle or a unit sphere. It may not be a unit sphere, but however much the radius is, it's actually centered that much above the of the xy plane, and ours is actually centered at the origin. So that makes it a little bit different. But nonetheless, we have still the same details, many of the same details as this particular problem. It says it wants the solid below the sphere, and it wants the solid, so it's trapped in sort of inside of the sphere, and it wants it to be above the cone. So again, it's sort of trapped inside the cone. So it's the sandwiched in area that you're seeing in here that we're going to be finding. So in a very real sense, it kind of looks like an ice cream cone with the ice cream on top, actually. And that's the volume we're going to be finding of this space inside of this particular object. So taking a look at these equations, then, we've got to take a look at how we're going to set up our limits of integration for our integral. So our integral, triple integral, and in spherical coordinates, and we're just taking, the integration of dv. So dv, so in fact, you know what, let me write it differently than actually I've just wrote it right here. So that we've got this set up actually to see the pieces better. So this is f of x, y, and z. And this is in over the volume, and our surface is, our solid shape is q. And we're going to do a triple integral. This is what I was trying to write earlier. Of dv, and dv is rho squared sine phi d rho d phi d theta. All right, so thinking about this image, we're going to try to create our limits of integration. Clearly, in terms of our equation for rho, our rho value goes from 0 up to 2, taking a peek, if you will, or thinking through the fact that our radius of this circle is 2, and of course our radius being rho actually has a minimum value of 0. The next thing that we're going to take a look at is d phi. Now d phi is actually defined to be the angle measure from the z-axis down. So in terms of our picture over here, my angle for phi, you can actually see it in here, is going to be measuring right this way, from the z-axis down to basically the edge of my cone. Now, the edge of my cone is actually going to make me this a measurement of pi over 4. And again, that's actually referencing back to an earlier example in this section, not one that I did on the iPad, but one that your book actually does. So if you want to reference that, you can take a look. But basically what happens is that in two-dimensional space of each of these, if you had z equals, and this is the square root of x squared plus y squared, it's forming like that 45-degree angle there. So we do in fact have from 0 to pi over 4. And then the last thing that we have to do is we have to do the angle between, the angle for d theta. So let's take a look at that. All right, so to take a look and think about how we're going to get those limits of integration, this is actually, if you'll remember, in the xy plane. So here's my xy plane. And the two pieces of information that I've yet to actually use are the y equals x and the x equals 0. So this is my y-axis, and I'm sorry. This is my y-axis, and this is my x-axis. Then the line y equals x, of course, is straight through like this. And the line x equals 0 is the vertical line going through here. So we actually want the angle measure between these two. Now, the angle measure at this particular point, at the point y equals x, is actually the angle pi over 4. And the angle up on the positive y-axis, of course, is the angle pi over 2. So my limits of integration actually go from pi over 4, on theta anyway, to pi over 2. And now that we have this set up, we're actually ready to do the integration. So we'll start in the inside, as we have been modeling all the way along. We're going to do the derivative with respect to, or the antiderivative with respect to rho. So this would be 1/3 rho cubed, and evaluate it at 2 and 0. And then we've got, oh, and I left off the other piece of it. It may not be changing, but it's still part of this value, sine of phi. All right, so putting the number 2 in, I get 8/3 rho, not 8/3 rho, 8/3 sine of phi. And now we're going to be ready to do the second limit of integration. So let's go back up and put the details on this one. Okay, I think I got all the details in there. Let's double check on that, but I believe I've got all the details in there now. The 8/3, of course, can come out in the front, so if you'd like, we can actually go ahead and move that to the beginning, just to make things a little bit cleaner. The antiderivative of sine phi, which actually is something we've already done, is actually going to be negative cosine of phi. And we're going to evaluate that at pi over 4 down to 0. And of course it's d theta at the end. Molly, stop! Sorry about that, guys. The dog's gone a little bit crazy over here. All right, so we're going to evaluate this. Another thing we could actually do too, just to make things simpler, is we could move this negative even out in front to make it a -8/3, which would be kind of nice. All right, so this is my screen with all my details. So I've got -8/3 integral from pi over 4 to pi over 2 of cosine of phi. And I don't think we ever actually did our evaluation, did we? No. So let me actually come back over here and do the evaluation before I start moving things around. I'll move the negative to the beginning, as I already did on this slide, but we'll actually evaluate this. So pi over 4 to pi halves. All right, so the integral of pi over 4 inside of cosine, that is the cosine of pi over 4, would be square root 2 over 2 minus, and the cosine of 0 is actually 1. So we have square root of 2 over 2 minus 1. And we're going to do that with respect to theta next, which is kind of nice because it doesn't even have a theta in there. Obviously, it's just going to end up being times theta, so I've got 8 over 3 times square root of 2 over 2 minus 1 times theta, and evaluate at pi over 2 and at pi over 4. Now the reality is, since we're plugging in the number pi over 2 and then to what this looks like, and it's just multiplied by the theta, and we're plugging in the pi over 4, when we do that, we actually end up just with the difference between the two. In other words, this piece is all stayed the same, and then we plug in theta and we get pi over 2, and then we plug in theta over 4 and we get, we plug in theta over 2 and we get times theta over 2, and then plug in theta over 4 and we get times theta minus the pi over 4, which is actually going to end up being pi over 4. So I've got -8/3 square root 2 over 2 minus 1, and this actually subtracts to pi over 4. Now we can actually reduce this 4 with this 8 to give me a 2, and we can actually put the pi in front with it if you'd like. So this is -2 pi over 3 times square root of 2 over 2 minus 1. Now some of you might be thinking, man, it looks like a really complicated mess. Isn't there anything we could do to simplify that? And there are some things that we can do. I'm not sure that's going to get a whole lot simpler, but we could certainly deal with that. One thing in particular is that I could multiply this 2 through over here, recognizing that this, of course, is going to be just the number 1. But if I multiply the 2 through, I get -pi over 3 times the square root of 2 minus 2. And that's kind of nice. I still seems a little bit odd because I've got all these negatives going on. So we could also distribute the negative and see what happens. So in particular, if I do that on this particular problem, I'm going to have, I can distribute the negative through the inside instead of through the outside, which would actually be a little bit nicer. And then I'll have 2 minus the square root of 2 right here. And that's our final answer for that problem. All right, one last example. All right, number 5. The last set of directions say the following. Evaluate iterated integral by changing coordinate systems. Just like we talked about last time, and the integral that we are given goes from -1 to 1 from negative square root of 1 minus x squared to positive square root of 1 minus x squared. And then this next one looks a little bit funny, but it goes from 1 minus the square root of 1 minus x squared minus y squared up to 1 plus the square root of 1 minus x squared minus y squared. And we're integrating x squared plus y squared plus z squared, all raised to the 3/2 power, dz, dy, dx. And as you can well see, this is not going to be friendly, if it even is doable at all in rectangular coordinates. We do like spherical coordinates though, of course, because you see that this is our rho value right here, so that's nice. In particular, rho squared, I should be more specific. All right, and then we also can take a look at these limits of integration. In particular, the innermost limit of integration is on z, and we have these two values. So my z value, it is actually going to be equal to 1 plus or minus the square root of 1 minus x squared minus y squared. Go ahead and resist the temptation of replacing the x squared minus y squared with r squared. Because if we actually move this 1 over here, z minus 1, we're going to have that, and then we can actually square both sides. So we'll end up having this piece right here. And then we can move the pieces around a little bit. So in particular, this will end up being x squared plus y squared. And then I'll have plus z squared minus 2z plus 1 equals 1. And this looks similar to something we found in cylindrical coordinates, I believe, in our examples before. This piece right here, not cylindrical coordinates, I'm sorry, it was in spherical coordinates. X squared plus y squared plus z squared is in fact rho squared. And then I have minus 2. Z is actually rho cosine phi. And then we have equals 0. And we can take our rho value and factor, so we have rho times rho minus 2 cosine phi. So my rho goes from 0 to 2 cosine of phi. So those are my limits of integration on rho. So that's my innermost limit of integration, actually. I need limits of integration on phi still as well. So just to identify this, keep in mind this is actually, this equation anyway, it is in fact a sphere, and it's a sphere that is centered at 0, 0, 1. We've got to shift up by 1 in the z direction because of this minus z here on the inside. With z over there, and it has a radius of 1. The next piece of information, we're actually going to work our way sort of backwards in our limits of integration, is that I have y is equal to plus or minus the square root of 1 minus x squared, and if I square both sides, I have y squared equal to 1 minus x squared, or x squared plus y squared equals 1. And this, of course, is a circle. It's a circle centered at the origin, but then of radius 1. So kind of like the last equation, you have x squared plus y squared equals 1 in there, but that one had a third component, of course, of z minus 1 squared. So this is a circle in 2 dimensions centered around the origin. And then I'm also being told that my my x values go from negative 1 to 1. Okay. All right, so let's take a look at taking our limits of integration and making alterations now. So we have a triple integral of rho squared to the 3/2 times rho squared sine of phi d rho d phi d theta. All right, so our limits of integration on rho, of course, we found before are 0 to 2 cosine of theta. So let me actually try this differently. Let me move that a little bit over. Man, I maybe need to move more for more space again later, but for now this I think will give us what we need. All right, so 0 to 2 cosine cosine phi, excuse me. Next we need to know our limits of integration on phi. So phi, of course, is measuring from the z-axis down. Now, the z-axis down actually has us going to be starting at z equal to 0, because this was a sphere, if you'll remember. And we're measuring down, but all of this was shifted up above the x-axis, so we don't need to go all the way beneath the x-axis. It will only go from 0 to pi, because this is all happening above the xy. Actually, from 0 to pi will get us down all the way to the sort of the negative z-axis, even though it's shifted up. But then spinning it around will get us the whole sphere that we were looking at earlier. All right, the last thing then is the spinning all the way around for theta. So this actually goes from 0 up to 2 pi. And the reason, of course, that it's 0 to 2 pi and not say something like pi over 2 to pi, or pi over 4 to pi over 2 like we had a moment ago, is because those limits of integration on, or sorry, not the limits of integration, but the limits of integration on y actually end up telling us, of course, that we're working with a circle. And the circle actually does include the negative y values as well as the positive y values, because we started out at the negative square root of that. If we had started out at, say, 0 or something, then we wouldn't have the whole 0 to 2 pi value. All right, so first we need to clean up all these rows. I have rho squared to the 3/2, that's rho to the 3, and then times rho squared, so this is actually rho to the 5th. And then I have sine of phi, d rho, d phi, d theta, and my limits of integration, which haven't, of course, changed. 0 to 2 cosine phi, 0 to pi, and then 0 to 2 pi. And we'll start out on the innermost integration. So, of course, rho to the 5th would be 1/6 rho to the 6th sine of phi. But we're going to evaluate at 2 cosine phi and 0. Of course, if we evaluate at 0, we get nothing. But if we evaluate at 2 cosine of phi, this starts to look like something we've seen earlier in this lesson. So I have 1/6. I have a 2 to the 6th, which is actually going to give me 64. And then I have the cosine to the 6th of phi and sine phi. All right, and so we saw this one before. This is actually going to end up being a u substitution on my next step. My u is going to be the cosine of phi, and then du in this case is actually going to be negative sine of phi. So let's go back in here. I got kind of getting a little carried away with myself. I need to put the limits of integration back on this guy. So I'm going to shift it over just a little bit here so I've got some more space. And I have integrals from 0 to 2 pi and 0 to pi, and it's d phi d theta. All right, so it's, of course, the 64 and the 6 can both reduce and be pulled out to the front. So if I reduce it, it reduces to 32 over 3, and I'll pull it out to the front, 32 over 3. So my integral from 0 to 2 pi, from 0, you know what, let's do the u substitution right now, and we won't have to write the 0 to pi. So this is actually going to be the integral. Well, you know what, I'll write it in just for the sake of having seen it once. It's not going to have those limits of integration because I'm replacing u. So this is u to the 6th now because I'm replacing the cosine. And the derivative of cosine, of course, is the sine of phi. So that piece also goes away, and then it would be du. And I've actually got the d theta still on the outside. So this is what we're going to integrate. Okay, so 32 over 3. Integral from 0 to 2 pi. Of course, the integral of the u to the 6th is 1/7 u to the 7th d theta. And then I'm going to use the actual value for u. I could go ahead and move my 1/7 to the front. I suppose that would be nice as anything at this point. So I had a 3 already out there, and there's a 7, so this is now a 21 at the front. And then u to the 7th would be the cosine to the 7th of u. And I think we're missing a -2, aren't we? Yeah, there's a negative right here. Oh, and I also didn't even write that down. My goodness, there's a d phi. So I did miss a negative when I was doing that. So the negative, again, can put anywhere, so I'll just put it at the very front to keep it kind of out of the way. And this is d theta at the end. Oops, first evaluate at 2 pi down to 0, and this is d theta then at the end. All right, so now we're going to integrate, or not integrate, but evaluate cosine to the 7th of u. So when I put in the 2 pi into cosine of u, I actually get 1, and of course it's 1 to the 7th, this is 1 minus. When I put in the value of 0,